At the core of every graph neural network, there is a simple idea. A node updates its representation by combining its own features with information from its neighbors. This process is called message passing. Each node receives so-called messages from adjacent nodes, aggregates them using a permutation-invariant function such as sum, min, or max, and then applies a learnable transformation. Formally, a node's representation at layer L+1 depends on the representations of its neighbors at layer L. Stacking layers expands the receptive field from one-hop neighbors to multi-hop neighborhoods. Message passing is the mechanism that allows structure to shape representation. I just want to make this parallel to convolutional neural networks, and I want to start by commenting that when we process an image with a two-dimensional convolutional neural network, each pixel updates its value by combining information from nearby pixels using the same filter everywhere. And this already is a form of message passing. An image grid is just a special, very regular graph where pixels are nodes and edges connect neighboring pixels. Neighborhoods are fixed and ordered. But when we move to general graphs, this regular structure disappears. Nodes have different numbers of neighbors and there is no consistent ordering between the neighbors. So graph neural networks replace convolutional filters with permutation-invariant aggregation, sum, min, max, or attention. What stays the same is locality, weight sharing, growing receptive fields with depth. Message passage is therefore a generalization of convolution to irregular graph structures. So continuing this discussion about the concept going from convolutions to message passing, I just want to say that 2D convolutions at each pixel aggregate the values of neighborhood pixels. So you deal with locality, or in some other words, you deal with a small receptive field, you deal with weight sharing because you are using the same filter everywhere, and you are using translation invariance because the same operation is used at every location. So when you move from the grid to a more general graph, what changes is that you have different number of neighbors from node to node. There is no ordering of neighbors. For example, you don't have the notion of a top left or a bottom right neighbor as you have in 2D convolutions. So fixed kernels are not applicable anymore, but instead you have to use some other form of aggregation. And message passing is a generalized convolution that keeps locality, weight sharing, iterative expansion of receptive field, and it replaces an order summation, which is the kind of thing you had in convolutional network, with a permutation-invariant aggregation. So if I comment a little bit more on the receptive field, in the case of convolutional neural networks, what you had in one layer was that each pixel was updated based on a small spatial neighborhood, and when you had multiple layers, you effectively expand the receptive field. In graph neural networks, you have exactly the same idea. With one layer, you are looking at one hop neighborhood and how that influences the update on the current node. And when you have L layers in a graph neural network, you are dealing with L hop neighborhoods. So it's the same mechanism, but it's a different topology. So going from convolutional neural network to graph neural networks, you do have the same abstract concept, but you are moving from strong geometry of the grid type geometry that you have in convolutional neural networks to a weaker topology in the form of a general graph. So here is an example where I'm looking at this target node A, and let's say that node A has feature as a feature vector this one 0 1 0 0, and when you are updating this node A, the update is being influenced by its neighbor. So in the case of this example, this is going to be influenced by nodes B, C, and D, because these are exactly the neighbors of node A. So depending on what feature vectors these nodes have, and depending on what feature vector the node A is, you have an update. And then you have a second layer in your graph neural network. So in that case, you are also going to have node A being influenced by the neighbors of nodes B, C, and D. So all of a sudden, you also have, for example, node F playing a role, because that's a neighbor of node D. So for example, here you are going to see that B is influenced by its neighbors D and A, D is influenced by B and F, because these are the neighbors of node D, and also by node A, and C is going to be updated based on node A. And node A then being updated based on this is also going to receive an influence from node F, which was not the case when you had a single layer. In the case of the message passing algorithm, what you do is you are starting with a graph, and let's say that you have n nodes in your graph, and let's assume that the dimension of the feature vector is d, meaning that you are going to deal with a feature matrix of dimensions n times d. This is another way of saying that this is a function that associates to each node v, it associates a feature vector of dimension d. So as I anticipated in the previous example, message passing happens in layers. So after one layer, a node's representation is going to include information from its neighbors. How exactly that information is collected, it depends on the type of graph neural network you are using, and that's something we are going to go into in the next videos when we discuss, for example, about graph convolutional networks and other types. After layer 2, you also have information from its two-hop neighbors, meaning neighbors of neighbors. And after layer k, you're going to have information being aggregated from all neighbors at distance at most k. So the initialization of these feature vectors is going to be based on the features. If I take again the example with the social media, you're going to have for each node, meaning for each user in your network, you're going to have some of their information. It could be age, gender, favorite book, favorite movie, hobbies, where they graduated high school, and so on. And then you go layer by layer, and the update of the embedding at layer k+1 is going to depend on what the embedding of that node was at layer k, and it's going to depend on something that aggregates the embeddings of its neighbors at layer k. So that's exactly what I was anticipating here, where I was saying that after each layer, you are going to have representation of embeddings of its neighbors. And these exact functions, what is this update, what is this aggregate, these are going to be some arbitrary differentiable functions, and they are going to depend on the type of network that you are choosing. And again, I'm going to have concrete examples when we start discussing about different types of graph neural networks. What's clear is that this function aggregate, which is applied to all of these neighbors, it's got to be permutation invariant, because its input is a set, it's not an ordered vector, so it doesn't really matter in which order the neighbors are presented, the results should be exactly the same. So here is an example. If I'm taking a citation network where the nodes are articles and the edges, you would have an H from U to V if article U cites article V. So after layer K, each article's embedding is going to reflect the local structure of the citation graph. It's going to see which articles cite other articles and going a path of length at most k. In the case of a social network, you would have in the nodes users, individuals, and in the edges you would have the friendship relation or the following relation, whatever that social media is really about. And you have this idea that the representation or the embedding of a node is going to be influenced by the representations or the embeddings of their friends. And after multiple layers, the information from the local community is going to become part of each user's embedding. And we will see when we start discussing about the first type of neural network that, for example, in graph convolutional networks, each friend is going to contribute equally. But this is just one example. There could be also other ways in which friends are updating your representation. I also want to mention just in passing that features can also be associated to edges, not just to nodes, as we discussed before. because the way messages are being passed from node to node depend on the edges. So you might have in some neural network some functions that influence how the message is being passed depending on the feature of that particular edge that you are passing through. And this is not something that I'm going to cover too much in these videos, but I just wanted to cover this, even if just in passing. Finally, I want to talk a little bit about how you move from node representations to learning tasks. And remember that we discussed in another videos that we are going to distinguish node level tasks, edge level tasks, and graph level tasks. So for node level tasks, these are tasks that concern giving some predictions about properties of nodes. And after you have a number of layers in your graph neural network and you have updating the embedding of that network, these node level tasks are going to be simply just some learner, whether it's a classifier or a regression, based directly from the node embeddings that you have after those layers in the neural network. If you have an edge level task, it's going to be exactly the same. You are going to have a number of layers in your graph neural network, and after that, to predict something about an edge is going to be about combining the embeddings of two nodes and having an extra classifier or regressor depending on what the property is that you want to predict. On a graph level task, you would have to aggregate all node embeddings into a single graph representation or embedding. And before we go into details, into types of graph neural networks, I also want to anticipate that there are limitations, and that these are limitations in principle of the graph neural network. So it's not a matter of implementation, but these are really a matter of their design, of how they're functioning. And the first one that I want to comment is that obviously graph neural networks, fundamentally they are about message passing, how you pass messages or embeddings from nodes to their neighbors. And this message passing is powerful. We made this connection to convolutions and convolutional neural network, but it's fundamentally a local mechanism. So what that means is that a node can only receive information from a limited number of hops, and that's going to be given by the number of layers. So that's going to have implications in terms of how much your receptive field is going to be. And on one hand, you don't want it to be too narrow. On the other hand, if you go for a too wide reception field, you are going to run the danger that all the nodes are going to see the entire graph, and so their embeddings are going to be fundamentally indistinguishable. So there is something very sensitive about this, and this is something that we are going to come back to into a separate video.